Hope you're all having a wonderful day, especially because it's Friday. I want to welcome you to the 134th episode of YFTT. It's Tech Talks by Engineers for Engineers. I'm Jim Nicely, a recently promoted distinguished engineer here at YB. Thanks. Uh, and so today we have with us Sfurti, a colleague of mine and a brilliant software engineer here at Yugabyte. And today she's going to discuss custom plugins in the YCQL Java Driver. I'm super excited to hear about any new features that are available to our customers. And so over to you, Sfurti.
Hey everyone, I am Sfurti. I work here in Yugabyte as a software engineer in the ecosystem team. And in today's session, we are going to cover custom plugins in the YCQL Java Driver. So basically, we are going to cover the various customizations that are offered by the YCQL Java Driver and how you can apply it to your particular use case. In today's agenda, we have the overview of the YCQL Java driver. Then we'll move on to the cluster discovery done by the driver. So this is important to understand as we move forward with the customization because cluster discovery is the backbone of all the customizations offered by the driver. Then it will be followed by some of the most important plugins and customizations that are offered by the driver, which will be followed by a demo and a Q&A session. But please feel free to ask your questions while we are going through the session.
Sfurti, so is the YSQL Java driver we're talking about, is that a jar file? Like, can it be used in dbeaver or db visualizer?
Yeah, it is a jar file, but the for dbeaver we already have Yugabyte DB as like we already have it as a connector there,
Right.
so you can just select Yugabyte DB by default. You do not need to modify anything there, but for DB visualizer it only takes JDBC connectors mostly, JDBC source connectors. So this driver also has a JDBC source connector in our repository. So you can use that for DB visualizer.
Nice.
Um, so moving on with the overview of the YCQL Java driver, it is actually fork of the upstream Cassandra data stacks Java driver, and it is the upstream driver is already highly efficient in parallel processing. It is very fault tolerant. It is an asynchronous driver, and it is very extensible, like it can be customized to your unique use cases in various ways. We offer two flavors of the YCQL Java driver. One is the 3.x version and another is the 4.x version. There have been few API changes between the 3.x and the 4.x versions. Hence, we offer both. The YCQL Java driver is modified with Yugabyte DB specific changes. So we have modified the upstream driver with certain Yugabyte DB changes. The first and the most important one is the partition aware policy. So partition aware policy is the customized load balancing policy in the YCQL Java driver. It is also the default load balancing policy of the YCQL Java driver. This policy offers optimized query routing by calculating the hash of the partition key of the query. So for each query, it calculates the hash of the partition key, and that hash lies between the hash range of one of the tablets of a particular table. We will discuss this partition aware policy further in detail as we move forward with the session. Next is the JSONB data type support. Cassandra does not have JSONB as data type, but Yugabyte DB additionally has JSONB as a data type. So YCQL Java driver also supports that. The cluster discovery done by the driver is the backbone of how the customizations will happen and how you can use them as the use case as per your use case. So how does it actually discovers the cluster? So when an app connects to one of the nodes in a cluster, this is the endpoint that is specified in the app itself. The node will send the cluster topology of that particular cluster to the app. So this cluster topology consists of two tables. One is the system.local table that contains the IP address of the node it is currently connected to, and next is the system.peers table that contains the IP address of the peer nodes of that particular node. Once the driver has all the nodes in that particular cluster, it will establish connection pool to each of the nodes. So now we'll move forward and discuss some of the most important plugins
So,
of the YCQL Java driver.
can I ask you a quick question? Like, how often is this discovery? How often is that performed? Like, what if a new node is added to the cluster?
Yeah. So first, initially, when the connection is made, uh, that's when the initial node, the cluster discovery happens. But in a case like when a node is added, the server sends an event change to the driver every 5 minutes or so, and the driver actually uh, uses a debouncer to query these event changes, and it has a delay. So after every event change, you can specify a delay after which it will refresh this particular cluster topology.
Great, thank you.
So the first plugin that we're going to talk about is the load balancing policy. So what is a load balancing policy? The load balancing policy determines which nodes the driver should communicate with for a particular query. We already have a customized load balancing policy for Yugabyte DB, as we had discussed earlier. That is the partition aware policy. Um, the load balancing policy can be customized further, but we have seen that partition aware policy is sufficient for most of the use cases pertaining to Yugabyte DB. So Yugabyte DB partitions table data into tablets and distributes it across all the nodes, and marks one as the leader and the others as followers. This particular table partitions and that replica addresses are stored in a table called system.partitions table, and this table is um, considered as the metadata for the driver. So the driver queries this table and stores it as the metadata. Um, then the partition aware policy, what it does is whenever a query is created, it calculates the hash of the partition key, and this hash lies between one of the hash ranges of one of the partitions, and based on that, the read or write query operation read or write query operations node is selected. So as we discussed earlier, the application creates a bound statement query, and the partition aware policy calculates the hash of the partition key from the query ID. So this hash lies between the start key and the end key of one of the partitions, and once we find which partition it lies in, we get the replica addresses, and one of the nodes gets selected, mostly prioritized by the leader, and it can be other nodes as per your consistency level.
Does every time you run a query, does it have to query this partitions table to find out where the leader is, or does it cache it somehow?
No, this partitions table is cached, and it is similar to what happens with the system cluster discovery. So, in case of event change, this partition, the data is refreshed.
Okay, makes sense.
So, the next plugin that we're going to talk about is the address translator. An address translator basically translates the IP addresses received from the cluster topology, like we had discussed earlier, into queryable addresses. So, into addresses that you actually want to connect to. So, for example, You have a 3 node cluster, and these 3 nodes are unreachable by your particular app. This 3 node cluster has a load balancer in the front, and the load balancer IP address is the only contact point specified in the app. So when the app connects to the load balancer IP, the load balancer will send the connection to one of the nodes, which will give it the cluster topology. But this cluster topology will contain the unreachable IP addresses, and when the driver will try to make internal connections, these will fail. Similarly, if you want the traffic to be routed through a particular zone only, and you do not want certain zones to be targeted at all, those zones can be translated into the preferred zones that you want to reach to. Usually local DC can be specified for that, but if you want further customizations there, but in particular nodes that you want to reach in particular zones, then this can also be a use case for you. By default, there is no address translation in the driver. And now let's look at the first use case that we had discussed earlier, where the load balancer was in front of a 3 node unreachable IP cluster. So in this case, what we would do is, when we get the cluster topology, the driver gets it. When it tries to make the internal connections, it will go through the address translator. Now, this address translator maps all the nodes from the internal IPs to the load balancer IP. So this address translator will map it to the load balancer, and all these channels will then be created to each of the nodes. So to implement the custom address translator, you just implement the address translator interface and override the translate and close methods. The next plugin we are going to discuss is the retry policy. Retry policy defines how the driver should react to different types of request failures. So, for example, in an event of a read timeout, a write timeout, or an unavailable exception, the default behavior of the driver, that is the default retry policy, is to retry once on the next host. So, when the driver sends request to one of the nodes in the cluster, and that node goes down, the driver will retry to send the request on another one of the available nodes. This happens only once as per the default behavior. But let's assume that you want to attempt more number of connections, or you want to increase the maximum number of retries. So instead of trying one, you want multiple attempts on other nodes. So you can implement a custom retry policy there. Another use case for you could be, if you have a 3 node cluster similar to the previous setup, and there is a load balancer in the front, and one of the nodes will go down. Since the app only has the load balancer IP, the driver will think that that load balancer IP is down, and it will try to retry to send the request on another one of the IPs, which it will not find, since it only has the load balancer's IP. Even when you have nodes available to send the request on, uh, the driver does not know about them, so it cannot send connections there. In this case, also a custom retry policy will help, which we will demo at the end of the session. Implementing a custom retry policy is the same. We implement the retry policy interface and override these methods for the 4.x version of the driver. Next plugin we are going to discuss is the reconnection policy. So, reconnection policies manage how the driver attempts to reconnect to down nodes until they are back up. So, the driver constantly tries to reconnect to the nodes that have gone down, And these can happen in there are two built-in reconnection policies. One is the exponential reconnection policy. In this, the delay between reconnection attempts increases exponentially. So the delay between each of the reconnection is exponential. And the other one is the constant reconnection policy, where the delay between the reconnection attempts is constant. The default here is the exponential reconnection policy. But let's assume a use case in which you have a YBA or a YBM cluster, and the cluster is under maintenance. Since you know it is under maintenance, you do not want aggressive reconnection attempts to that particular cluster. So you can and create your own custom reconnection policy, which checks once the cluster is out of maintenance, and it will try reconnecting then aggressively, and before that you want it less aggressively to try reconnecting it. And similarly, if you want a node distance based reconnection, so you want like the local remotes to be reconnected to more aggressively if they go down rather than the remote nodes. In that case also, a custom reconnection policy will help you. So implementing a custom reconnection policy is also the same. You implement the reconnection policy interface and override the new schedule method.
I was going to ask, is there a point where the driver kind of gives up trying to reconnect, or is it just go on forever? But I guess that's why you have the one, you're having maintenance, right? So you don't want to aggressively go.
Yeah.
Is it kind of that?
Yeah,
Okay.
so it does do it infinitely, but in the maximum sorry, exponential reconnection policy, which is the default, after a certain number of attempts, instead of increasing it infinitely, you can uh, customize the driver to basically send a config called max delay, and that
Okay.
max delay is then after certain attempts, that is the only delay after which it will connect, like it will become constant.
Gotcha. Okay.
The next plugin is the speculative execution policy. So this policy allows the driver to send speculative requests to additional node if the first node is slow to respond. So for example, you want to reduce latency in your environment where some nodes are slower than the others. So the connection on the requests on those particular nodes, uh, if they are slower to respond, can be sent speculatively to other nodes that are faster. Similarly, in case where your consistency level is quorum, and for your read or write operation to be successful, you want two of the three nodes to respond. So if one of the nodes is slower, you can speculatively send the execution on the other node that is available, and that can help you achieve quorum faster. By default, there is no speculative execution, and this can also be customized to specific queries. So if you want speculative execution to only happen to certain queries, you set the execution policy with one of the execution profiles, and then you set the execution profile to that particular query. Implementing the custom speculative execution policy, you implement the interface, the speculative execution policy interface, and override the following methods: next execution delay and close. The next plugin is the node distance evaluator. So node distance evaluator is a customization offered by the 4.x version of the driver. It allows to customize how the driver calculates the distance between nodes and marks them as local, remote, or ignored. So local is the more preferred zone. Remote is lesser in priority, and ignored is where the driver will not try to where the driver will not try to send requests to these nodes at all. So a node distance evaluator can be mostly used where you want to give priority to a certain set of nodes. So you want to connect to specific nodes, or you do not want to connect to specific nodes at all. Node distance evaluator can be used. Similarly, if you want to give certain nodes more priority, then you can mark them as local and the other nodes as remote, giving the nodes in your preferred zone uh, priority when executing a query. And in similar way, if you want connections to not go to certain nodes at all, you can mark those nodes as ignored, and um, those nodes will not be the connections, the requests won't be sent to those nodes at all. And so by default the node distance is calculated based on the local DC. So the um, distance the local is the uh, nodes in the local DC, remote is the nodes that are not in local DC provided.
Sfurti, does that mean does it compare the value in the data center column of the system local table of the node? Like if you, how does that work again? Like how does it
Yeah.
determine which is local and which is remote?
Yeah, so right now for the 4.x version of the driver, local DC specification of the local DC is not mandatory. So if you if the node connects to whatever the app connects to one of the nodes, whatever the data center of the node is, that will be considered as the that will be considered as local.
Okay.
And if you have specified local DC, then in that case whatever local DC specified, nodes in that will be considered as local.
Okay.
So implementing a custom node distance evaluator, you implement the node distance evaluator interface and override the evaluate distance method. Next is the whitelisting nodes plugin. This is one of the plugins in the 3.x version of the driver. So this is also similar to the node distance evaluator, where it allows you to target specific nodes in a cluster. In this, you can give those particular nodes that you want to connect to as part of the whitelisting node configuration, and you can target whatever your preferred zone is. So implementing whitelisting in 3.x driver is a little different. You create a new instance of the whitelist policy class, which is actually a load balancing policy class, and you pass the whitelist node as the configuration for this instance. Then you set the load balancing policy to this particular instance. So moving on to the demo part of the session. For the demo, we are going to showcase two of the custom plugins that we have discussed earlier. One is the address translator and retry policy. For this, we have the setup similar to what we had discussed. We have a 3-node Yugabyte DB cluster. Each of the node is a Docker node, and there is an HA proxy load balancer in the front. This entire setup is running on a separate VM from the app that is actually running, and this app only can connect to the load balancer, and the internal nodes are unreachable to it. The as For the application, as I specified, it only has the IP address of this load balancer, and what the app is doing is basically running a lot select statements in an infinite loop. So in this, we are going to discuss three scenarios. We have an application with default behavior, that is, we do not have any address translator, and the retry policy is the default retry policy. So in this case, as we had discussed earlier, the initial connection pool to the internal nodes will fail because there is no address translation and the internal IPs are unreachable. And when one of the nodes go down, the load balancer IP will be thought as down by the driver, and when the driver will try to send request on another node, it will not find any, as it does in default retry policy. So for the first issue, that is the initial connection pool to internal nodes failing, we introduce a custom address translator in our application. This will make the internal nodes reachable by translating the internal nodes to the load balancer IP. But when one of the nodes will go down, it the app will still fail because the driver uh, because the driver will think that the load balancer IP is down, and since all the internal connections are also pointing to the load balancer IP, um, the driver will not find any other node to send request to. So for that we have introduced a custom retry policy. So instead of finding another node to try to send the request to, the driver will try to send the request back to the so try on the same IP address, that is the load balancer IP address. So since the load balancer IP address is not actually down, the request will not fail and it will pass. So let's start with the demo. We have this default application here. We're going to run it. As you can see, the retry policy class is default retry policy. um, you can see the first issue here, the internal nodes that it is trying to create a channel to, it fails with the error opening while error while opening new channel. Now we will stop one of the nodes and you'll see the app instantly fails. This is because it tried sending the request on a different node, but there was no different node available to the driver. So the app will immediately fail here. Now let's restart the node, and we have this application with the customizations. Basically, we have the address translator and we have the retry policy as custom retry policy. So you can see here the retry policy class is custom retry policy. Now you will see the first issue has disappeared. You can see translating hosts. We do not get error while opening new channel. That is because the internal nodes have been translated to the load balancer IP. Now we'll stop the node.
It's cool to see this all in action. I think we have about a minute left on time, by the way.
Yeah, we're just done with the demo. And now you will see the app runs just fine here. So what it did was, instead of trying to connect on a different node like the default retry policy does, the driver connects on the same load balancer IP as per our custom retry policy. And since the IP is not actually down, uh, the load balancer will send the request to the remaining nodes. So you can see we have this attempt close connection exception and attempting retry on the same node. So that was all for the demo. Um,
That's
Thank
great.
you all. Yeah. Do star us on GitHub and join us on Slack. Thank you.
So you mentioned there's two different versions, right? A 3x and a 4x version. So when a customer is deciding which one to go with, it's based on features available, I guess, not on performance. There's no performance difference between the two, maybe. Or just more in the
Um,
features. The API, I
so
guess.
yeah, APIs are different, definitely, and 3.x is a little less modular, and it has a little less versions of customizations in in connection pooling, and even these customization it is a the 4.x version is a little superior in these things. So if you have like a legacy application, then 3.x is fine. But if you want more modularity, more customizations, then go for the 4.x version of the driver. That is the newer version actually.
Cool.
So that would be better.
Well, thank you very much. It was a great demo. I don't think there's any questions, but if you guys have questions, right, you can, like on Slack, you can join us on Slack, or once I think it's available on um, LinkedIn too. You can put some questions there. But yeah, thanks everyone for attending, and I hope you enjoyed it.
Thank you, everyone.
That was great.